If you want to run a strong AI on your own PC, this is the split-second question. Do you pick Qwen 3.6 or Gemma 4? By the end, you'll know which one fits your hardware and your use case. No guesswork. Before specs, remember, local AI success is mostly about friction, not slogans. I remember the first time I tried to run a big model locally. It wasn't even about intelligence. It was about friction. The prompt felt fine, then the speed tanked, or the model refused to behave the way I expected in an agent setup, or I loaded the wrong format and the whole thing was a mess. That's what makes Qwen 3.6 vs Gemma 4 tricky on a consumer PC. Here's the real deal. On paper, both are strong, but on your machine, the win usually comes from four things: model format, context length, tool/agent behavior, and speed under your settings. So in this guide, I'm going to treat it like engineering, not like hype. We'll start with what Qwen 3.6 actually is, then what Gemma 4 tends to be optimized for. After that, I'll show you how to decide based on your GPU and what you want to do: coding assistant, long context notes, or tool using agents. But wait, there's one detail about Qwen 3.6 that changes the way you plan the whole stack. Let's get there.
Qwen 3.6 isn't just another LLM, it's engineered for long workflows. Let's anchor on Qwen 3.6 first. The model family Qwen 3.6 is described in an open-weight format, with weights and configuration files you can use in the Hugging Face Transformers ecosystem. Spec-wise, Qwen 3.6 for this guide, Qwen 3.6-35BA3B is listed as a causal language model with vision encoder. It also states 35B total parameters but 3B are activated. That activated BS total detail matters because it often correlates with how the model behaves during inference, especially in mixtures. And then there's the context. Qwen 3.6 states a native context length of 262,144 tokens and says it's extensible up to 1,010,000 tokens. You don't need that maximum every day. But if you write agents that browse your own notes, or you paste long logs, that headroom changes the workflow. Finally, the architecture includes mixture of experts. It lists 256 experts, with 8 routed plus 1 shared active. This is one reason people pay attention to Qwen 3.6 for coding and agentic setups. The model's documentation also emphasizes stability and real-world utility, including an agentic coding focus. Now, what does that mean for you practically? It means Qwen 3.6 is built to be usable, not just smart. You can plan for longer sessions, and you can build workflows that keep reasoning context from historical messages because it introduces a thinking preservation option. But wait, Gemma 4 is not the same story. Let's compare on the quality benchmarks and what they imply for consumer hardware decisions. You can't pick a model from Vibe's benchmarks hint at the real difference. Now let's talk Gemma 4, but carefully. I'm not going to pretend the choice is purely about numbers. Still, benchmark tables are useful because they show where each model tends to land. On the Qwen 3.6 model page, there's a benchmark comparison table that includes results like SWE Bench Verified. It lists Qwen 3.6-30 5BA3B at 73.4 versus Gemma 4-31B at 52.0. Another line shows Terminal Bench 2.0 with 51.5 for Qwen 3.6-35BA3B versus 34.2 for Gemma 4-26 BA4B. And for general knowledge-ish tasks, it lists MMLU Pro at 85.2 for Qwen 3.6-35BA3B and 85.2 for Gemma 4-31B. There's also GPQA at 86.0 for Qwen 3.6-35BA3B versus 82.3 for Gemma 4-26BA4B. Here's the insight I want you to take away. If your primary goal is coding reliability and tool-like behavior, think generate code, run it, fix it. The benchmarks shown there lean strongly toward Qwen 3.6. But if your goal is balanced general reasoning with a simpler deployment, Gemma 4 can still look competitive on some knowledge benchmarks. So how do you turn this into a consumer PC decision? You combine quality with practicality. How you quantize, how you run, and how speed behaves under your settings. Which brings us to the biggest trap: formats and speed hacks. Let's do that next. Most people fail locally because of formats, not because the model is too big. Here's the part nobody explains clearly. Your model isn't one thing. It's a pipeline. For Qwen 3.6, there are artifacts specifically labeled for quantized formats. One repository on Hugging Face is Qwen 3.6-35BA3BFB8, and it states it provides FP8 quantized model weights. It also describes the FP8 quantization as fine-grained with block size of 128. It further claims the performance metrics are nearly identical to the original model. Now, I'm not telling you to blindly trust the claim, but it tells you they're thinking about preserving quality when reducing precision. For ultra-local setups, there are also GGOF examples. There's an unsloth GGOF repository that explicitly describes an example of Qwen 3.64-bit GGOF running in Unsloth Studio with tool calling. And one key detail: the same GGOF repo claims tool calling improvements, specifically making parsing of nested objects succeed so tool calling doesn't fail as often. Now, a warning because local work is full of gotchas. Some variant pages mention that Hugging Face's hardware compatibility widget may not recognize certain KP quants and suggests using the View plus X variance approach. So your job isn't just pick Qwen or Gemma. Your job is pick a format you can actually run on your GPU, with a runtime you can control. Let's talk runtimes and the fastest path to your first working result. If it feels slow, don't immediately switch models. Try the decoding lever first. If you've ever said this model is slow on a consumer PC, you're not wrong, but you might be missing a lever. There's a speculative decoding approach called dflash, described in a repository for Qwen 3.6-35BA3B dflash. The page defines dflash as a speculative decoding method using a lightweight block diffusion model that drafts multiple tokens in parallel. The quick start shows an example via LLM launch that uses speculative config with method dflash and a speculative token count. More importantly, the benchmark section reports up to 2.9x speedup at concurrency 1. It also gives an example in a throughput table where Math 500 has a higher AR score with dflash. Here's the insight: this doesn't mean your PC will always get 2.9x. Speed depends on your runtime, prompt pattern, and settings, but it proves a key point. Model speed can improve without changing the model's identity. So when you decide Qwen 3.6 vs Gemma 4, don't just compare raw quality. Compare how fast you can make it usable with your runtime. Now, let's get specific about what to test first on your PC so you don't waste hours.
Here's the fastest way I decide: use case first, then format, then runtime. Let's turn this into a simple checklist you can actually use tonight. Step 1. Define your use case. If your workflow is mostly coding plus agents, generate code, run tools, iterate, Qwen 3.6 has a strong argument. The benchmark table shown on its page leans toward Qwen for SWE bench verified and terminal bench. Step 2. Define your patience for setup. If you want the fastest, it runs in a UI experience. Sometimes Gemma 4 can be simpler depending on the ecosystem you use. But you still must check quantization availability and tool calling support in the format you plan to use. Step 3. Plan for context. If you often paste long logs, large docs, or maintain multi-step planning, Qwen 3.6's stated native 262K context and extensibility can reduce your truncation pain. Step 4. Check your runtime stack. Qwen 3.6 is described as compatible with Hugging Face Transformers, VLLM, and SGLang and others. That's useful because it means you can choose the runtime that best fits your GPU and your target latency. Step 5. Test with one real prompt. Don't test with write a poem. Test with your thing. Like, read this error log, propose a fix, generate a patch, and keep the explanation short. Measure output time and retry rate. But wait, there's a detail that can make or break your agent tests. Tool calling and nested parsing. Let's close with a practical testing script you can run in 10 minutes. Run these 4 prompts and you'll stop guessing which model is better for you. Here's how I test on a consumer PC. No theory. Just signals. Test 1, the speed plus coherence check. Ask for a small coding task with one constraint. For example, given this code, identify the bug and output only a corrected diff. Time it until the answer arrives. Test 2, the tool calling check. Ask the model to produce a tool request with nested fields, then see if it stays valid. If the format you're using supports tool calling, you'll notice quickly when JSON or nested objects get mangled. For Qwen 3.6, there are GGUF examples that explicitly mention tool calling and nested object parsing improvements, which is exactly why this test matters. Test 3, the context stress check. Give it a long chunk, like 20 pages worth of notes, or a long log, and ask it to summarize with references to specific sections. If it truncates silently, you'll feel it. Test 4, the reasoning continuity check. Run a multi-turn session where message history matters. Qwen 3.6 introduces a thinking preservation option, so if your workflow benefits from retained reasoning context, you'll see it. Then compare results. Not just who is smarter. Compare retries, time to correct output, and how often the model drifts from your constraints. That's the truth serum. And once you do it, the choice becomes obvious. If you want, I can share a concrete local setup workflow in the description, including what I test first and how I pick formats for my own machines. Mnemonic workflow link is there too, by the way. Subscribe for more of these consumer PC comparisons, because the next one will be even more practical. If you want, I'll link a practical workflow in the description, how I run and test local models step by step. Subscribe if you want more consumer PC guides like this. And yes, stay to the end, because the last tip changes the results fast. Made in 90 seconds with Mnemonic.